Hi there. Today I am going to be describing the project that our team tackled for the spring and summer 2020 Capstone. We were sponsored by Jim Blandy, and our project title is called Rust Console Tester. A quick gloss over the members. We had 6 in all, with Shawn Hice in charge as the team lead, Brad Hopper, Ian Gauldin, Grady, Nick Hanemann, and me, David Meyer.
Hello, my name is Shawn Hice. I'm going to be going through a quick overview and then through a demonstration. So the Rust Console Tester is a developer test framework that enables Rust developers to test the consistency of their console user experience. I'm going to show you what that means in a second. Hey everybody, so right now what we're going to do is we're going to walk you through how to actually use the crate that we developed as part of our Capstone project. And the crate we developed is called Console Tester, and it's available for everybody through the Crates package management service. And I'm going to show you how to download that real fast and what you need in order to get it running. So right now we're in Visual Studio Code, and we're going to go over into our cargo toml file. And in order to add the crates.io like dependency, we're going to go ahead and type in console tester with an underscore, and I'm going to supply a version to it. And the version you find off just the crate's website, as you normally would with really any kind of crate, which is a fantastic way to actually retrieve files. But right now I don't actually need that because this dependency is already fulfilled by another crate. But you would normally need that. So let's walk through a little bit of strategy here. So you're a systems designer and you want to design a very specific system requirement, and you're printing out a bunch of information to the console. And for instance, right now I'm a very great systems engineer, and I'm going to print hello world to the console. So if I run this program using cargo run, it will print out hello world at the very least, because that's what I'm asking it to print out. However, if I had a very large program and I had a bunch of data that I was printing out, and I had very specific hardware cues like make a sound or make some kind of exterior hardware item shake, etc., things like that, I would need to supply it actually specific data in order to get all of that information to go to the terminal. So how to supply that data is using a byte stream. Down here you can see an example of one type of data that's actually being supplied in order to make some kind of other noise or some kind of other symbol that's not regularly accepted into a normal string. So 27, 79, 68 is a sequence of escape codes that actually will work on Xterm, and Xterm is a very common terminal that many people use on the Linux systems. So what we're going to do right now is we're going to walk through what TermWriter and TermStrings are, which are both part of the library that we've created. Now TermWriter, what it does is it allows you to, instead of using print line, it allows you to concatenate all of your output and instead write it to just one object. And this object will store all of it so that you can compare it against TermStrings. Now TermStrings, what it does is it stores all of the capabilities and all of the information about what a terminal can use within a certain document. And we pull that document and we say, hey, based off of this terminal, can we actually use this string and will it print good data? Now what I mean by good data is, will it print any malformed strings? Will it give me any errors? Will it give me anything that I'm not expecting to see or a user to see? Now these things can be very difficult to test, as you can imagine, but we'll go into that later. So right now we have a buffer write with this sequence of characters, and we have hello world appended to that. And what we're going to do is we're going to add a path, and this path is just a relative Xterm path, and we're going to load it into TermStrings. Now this will be supplied with the actual crate when you download it, essentially, or sorry, when you add it to your cargo toml file. And I'm allowing it to create a TermStrings from path, but you can also create a TermStrings from your local environment without supplying it a path at all, so it can use your local console to test things instead. Now, that can be unpopular for a wide range of reasons, but mostly because ideally you're testing against multiple different terminals and seeing if any of them fail, but we'll go into that in a second. Right now, I'm using the buffer, and I'm using a method called compare within the buffer. And what this is doing is it's taking in a TermStrings. And in the back end, what it's actually doing is it's comparing these two using regular expressions to see if there's anything in here that TermStrings doesn't recognize. And if there is, it will give us back a failure code, and it will tell us exactly what it didn't recognize. Otherwise, it will return true. And you can see, as an example, I've already returned true once, but let's run it again just for testing sake. Yep, so it returns true. Now, what I would like to do is I would like to actually get it to return false. Now, I can do this pretty easily by malforming some data, but as you can see, it's probably pretty easy to recognize where someone might accidentally do this wrong, and it would be very, very difficult to tell depending on how deep in the console you'd actually have to go to test this, and it would require a lot of resources to do so. So I know, for instance, that this will give me a failure, and this is what our crate will give you. It will indicate to you where the failure happened by showing it in brackets, and it shows you that there's an escape sequence that right now is being recognized as 0 greater than symbol, my guess, with a whole bunch of XOR concatenated data. And then it will return you an error that says that there's potentially unrecognized escape sequences in what was found. Now, this would be absolutely fantastic in an automated test kind of scenario where you have different tests that say, hey, I'm going to test this on Windows versus Mac versus Linux, and on the different terminals within each of those systems. So, what you'd actually need to do to test all of those things is, ideally, you'd create separate tests and then copy over the data from a buffer into these term writers. But I'm going to use the clone trait that was extended onto our term writer. And then, once I've cloned it, what I'm going to do is I'm going to add a new terminal strings file real fast so that I can add a new compare function to now what is this new buffer that contains all this previous data. So now I want to say, hey, this failed on xterm, will it also fail on sigwin? And my guess is yes, because it's kind of a random set of numbers. But if I save this and I go and do, oh, hold on one second, I want to make sure that I print out a result. If I do cargo run, you'll notice that I get 2 console failures. Now, this would be really, really great if I had 2 different tests here, like I was mentioning earlier, and those both, returned on Travis or GitHub in the continuous integration and said, hey, right now you're failing on Windows or you're failing on sigwin, but on Linux through xterm it's perfectly fine. There might be a bug in the code that is returning some malformed input. So, maybe I go back as a developer now that someone's logged that bug, I fix the error and I run it again. So now when I run it again, you can see that, hey, it's only failing on the actual second one. So this is a path recognized, or this is a set of integers recognized by xterm, but it's actually not recognized by Windows at all, which is very interesting. And what I mean by Windows is sigwin, which is a Linux emulator on Windows. It's a very special type of terminal. But that's very interesting, and that's something that I think a lot of developers look for, and that's something that, Jim will also talk about later, our sponsor, as part of the Rust community and what they're looking for. Anyways, well, thank you for your time, and let's continue.
Now, the purpose of the Rust console tester is to test consoles for Rust developers. That's a pretty tongue-in-cheek description, but what's that really mean, to test a console? Our team was tasked to create an aid that would allow Rust developers to test their console code on multiple different terminals. This tool will help them create a consistent user experience and give them a better understanding of how their output is displayed. To give a little more context, when it comes to displaying data, not all terminals handle output in the same manner. One might find that a particular escape sequence is properly displayed through terminal A, but the same is not the case for terminal B. Thus, the developer may be required to configure these escape sequences differently for different environments. This can be a source of frustration for those that desire consistent output across the board. By providing a means to compare expected against actual output on a selected terminal, we hope to expedite the testing process. Why do this? Currently, there is no cargo crate for Rust that allows its users to perform these kinds of tests. Our goal in creating the Rust console tester is to provide a proof of concept and to take the first step towards bringing the capability to Rust programmers. Rust is a fast-growing language, and it has a tight-knit community. People all over the world are contributing to thousands of open-source projects, and just this June, Rust broke into the top 20 programming languages. So who wants this? As the Rust community continues to grow, software built from Rust will have a greater reach. New testing tools for large projects will be in high demand. Those seeking to build a better platform, both by and for Rust users, will want to ensure a comprehensive suite of these kinds of tools is available, especially in the case of our project, which aims to bring a more reliable experience across various platforms. The idea behind this crate is fairly simple. It's going to take in some data, find any bad patterns or escape sequences, and output that data with the bad sections highlighted. We wanted to keep it as simple as possible to encourage maximum usage. If you forget to select which console to test against, it just uses the current one. No bad data, we don't have to highlight any bad data. All you have to do is grab it off crates.io, feed it some input, and it does all the parsing and analysis for you. You can even test against multiple different terminals at the same time. Going into a little more depth, we see here a user on the left who gives his input to our tester. Say, for example, a text file, which they want to test against the Xterm terminal emulator. Two things happen at this point. Data goes into the TermWriter object, and the term_string object seen below goes and fetches the known good escape sequences for Xterm. The compare function is then called and uses regular expressions to parse the data to be compared, and our output in the green will either give us the AOK or show us where the bad data is. The following slide gives a little snapshot of what a test that went well might look like. When it comes to what the future might look like for this kind of project, the most obvious direction would be to display as much relevant information as possible. There's a big difference between simply highlighting the bad parts of the input and providing a solution. For example, hey, X input will fail to display properly on Y terminal. Here's how to fix it. Another direction would be to add additional files for lesser known terminals. But at the end of the day, our goal is to create something useful, needed, and simple to use. Another tool for the box to make life easier. From here, I'll pass it off to the other team members who will go over how the crate was built.
Terminfo files, which are the successor to termcap files, hold information about what a specific terminal's features are and what a terminal is capable of in values known as capabilities. A typical terminfo file contains three types of capabilities. First, there are booleans. These are the simple yes or no capabilities, such as whether or not a terminal has automatic margins, or if the terminal can redefine existing colors. These values are always true. If they are false, they simply don't show up in the file. Second, numerical capabilities. These are used for representing capabilities described with numbers in the terminal. Some examples of this are the maximum colors supported by a terminal, the line and column counts, print rates, and more. Finally, strings, which represent terminal symbols. They are capabilities that perform certain actions, such as moving the cursor, clearing the screen, and entering or exiting insert mode. Since terminal symbols are only represented as strings within terminfo files, we do not have any need for numerical or Boolean capabilities in this project, so we needed a way to filter out the strings into a structure that we can use. The termStrings struct uses the terminfo crate to load a terminfo file, either from the environment using new from env, or a specified path pointing to a terminfo file using new from path. From this, it strips out the numbers and booleans. With this vector of strings, check valid symbol can be used to determine if a given terminal symbol is valid or not. In the future, this project could expand to a more complete console capabilities tester by making use of the numeric and Boolean fields within the terminfo files.
Hi, my name is Grady, and I was responsible for most of the implementation in the Buffer.rs module. So the first thing that I want to talk about is the write trait implementation for the TermWriter struct. So I had two different functions of this write trait implemented. The first function is a write function where it takes a user's applied input or string, writes it into the TermWriter object in the form of a buffer, and then returns the number of bytes successfully written. Having this write function implemented makes it easier on the user because they don't have to worry about knowing the underlying workings of the TermWriter object. All they have to know is the specific input that they want to test. So all they have to do is take the write function, pass in their input as the argument, and then the TermWriter object along with the supplied methods will handle the rest. The second write trait function that I implemented is the flush function, and all this function does is it takes the buffer data written to the TermWriter object and empties it to the final sink. The second thing that I want to cover is the TermWriter struct itself. I had implemented two methods for this struct. The first function is a new function where it instantiates a new TermWriter object when called. And then the second function is a compare function where it takes the user supplied string or input and then compares it against the terminfo database list of valid escape sequences. The first iteration was implemented by myself, but this function was finalized by Nick because of his close tie-in with his Reg.rs module. The third and final function that I implemented is the error print function. This is just a print function that shows the user exactly where in their supply string failed to parse when compared against the terminfo database list. This function was implemented because we were not happy with the vague error message that we had initially. We wanted to give better feedback to the user so that the user knows exactly where in their supply string the error happened, so which sequence of characters or the string was invalid. Keep in mind that this error print function is not a direct part of the TermWriter struct. It is more of a supporting function that resides outside of it. The third and final thing that I want to discuss are the feature improvements that could be made to TermWriter. First and foremost, I could see file I/O being added, so reading from file and writing to file. I think doing so would make it so that TermWriter is no longer restricted to requiring user input to operate. It can then operate with files as well. The second improvement I can see being made to TermWriter are additional instantiation options. So for example, with the read from file implemented in the future, we could have another new function that takes a file object as an argument to instantiate a TermWriter instead. And that way we do not require user input for TermWriter to operate.
The Reg.rs module is where we look at the user input obtained from TermWriter and the list of escape sequences found in TermStrings, and we compare them to verify that all escape sequences in the user input are valid with respect to the chosen terminal. Our first step uses Rust's regex crate to look at both the user input and the escape sequences list and remove all valid escape sequences from the user input. Our second step is to verify that after all valid escapes are removed, no escapes remain. This is done by examining every remaining character and checking that none are designated control characters. If this check is successful, the comparison will return a positive result. If this check is not successful, the user must be informed about what caused the failure. We set up a number of error return types for different types of errors, including one that sends back a modified version of the original user input. This modified version contains the user input with all valid escapes removed, and all remaining control characters, which indicate invalid escapes, are replaced with a plain text representation of which character failed. For instance, the character that begins most escape sequences, represented in code as \x, would be mapped to its standard ASCII abbreviation of ESC. Potential future improvements for this module mirror the issues we had developing it. For instance, there exist some escape sequences which do not follow standard practice and do not contain control characters. In the end, we decided not to handle these outliers as it would be extremely difficult and time-consuming to account for them without returning false positives. Figuring out an elegant way to handle these would be a good improvement for the future. Additionally, providing information about invalid escapes was a major issue. While we solved it, our current implementation only works particularly well as a human-readable error message. Notably, it does not include indexes of errors in the original input, because we detect the errors after modifying the input. Rust's regex crate is not able to give all the information needed to compensate for our modifications, so for perfect error messages, the whole algorithm would need to be redone using something else.
Hello, I'm Ian, and I'd like to talk about packaging and distributing our project. Our main distribution channel is Crates.io. Now this was an easy decision, as Crates.io is the package manager for the Rust ecosystem, much like NPM for the JavaScript world. With our project on Crates.io, our package can be included in anyone's cargo.toml file, which is the Rust config file, and automatically pulled from Crates.io and built. In addition to package hosting, our documentation is also hosted through this process on docs.rs. And another thing that makes it an easy decision was that it's already integrated into Cargo. Cargo is the package manager command line tool for the Rust ecosystem. So distributing your app through Crates.io using Cargo is batteries included and requires very little configuration to actually get going and published. Additionally, from being Crates.io, our project is also mirrored on Lib.rs, which is an alternative package repository for Rust libraries, which seems to just do a scrape of Crates.io, along with looking through GitHub repos and the internet in general to find more Rust projects for everybody to see. Additionally, we had discussed hosting packages on GitHub, which is something we can do, but I didn't really see much advantage to it. We expect Crates.io to be the main avenue to accessing and using our project.
I think that with any project, there are going to be problems that come up, and this project wasn't really an exception. We had a lot of difficulties with certain things during our development, especially because this had a lot of research involved with it. No one's ever really attempted to create something like this before, so really, I think where we persevered and came together as a team was when everybody really focused on doing the research and figuring out what was possible and designing our subsystems and our research topics around that during the first quarter. And then in the second quarter, you know, everybody picked up the slack and we got together and we figured out, hey, what is the user experience? What is it going to look like when Grady writes TermWriter, and what kind of traits should we implement? How are term strings going to be derived, and what kind of future improvements do we need to make? And defining those kind of stretch goals really helped us get through this project with almost no problems during the very end. There were certainly management issues that we had to work around, such as managing the sprints and designing our sprints to actually encompass research topics, which isn't a very regular, normal thing to do. So I believe that through the hard work of all of our developers, and especially David, our user experience person, that we really developed something special, and I think that overall it was a fantastic opportunity for us. I'm going to let Jim speak a little bit more about the original intentions of the project and why something like this is important to the community.
Yeah, well, the reason that I submitted the Capstone proposal in the first place was that there's this real missing piece in the Rust ecosystem. One of the things that Rust is used for as a systems programming language a lot is to write, console programs. These are the kinds of programs that system administrators would use, that software developers would use, and they're not necessarily GUIs, right? And they're not necessarily web apps. These are things that you use directly from the console on your computer. And sometimes, a lot of times, the interaction between a program and the console is pretty simple. But sometimes you want something that goes further, that has like a nice interactive display, or a live display that updates information as things change. And all of those things require interacting with the console in a more complicated way than is usually supported. And the wrinkle in all of this, that's all fine, but what makes it interesting is that different consoles want you to interact with them using different sorts of escape codes. If you're on Linux, then you want to send one set of escape codes to the console to control the screen, to get the display to look the way you want. If you're on Windows, it's a completely different set. And actually, even on Mac, it's a third set. And actually, even on Linux, there's a variety of different consoles that people might use. And so it's very difficult to test programs to make sure that they work on all these different platforms. And what's really great about this Capstone project is that it's a foundation for a way to test one program against all these different kinds of consoles in a very simple way. It makes it really easy for people it makes it really easy for developers to write tests that make sure that their program works on a variety of consoles. And since writing console programs is something that people do a lot in Rust, this crate, by making those programs easier to test, is a valuable contribution to the Rust ecosystem.
I wanted to give a special thank you to everybody who really made this project happen, and I thought it was so much fun and it provided a really interesting program to be developed by us. But especially thank you to Jim. He was amazing throughout the whole experience, and he really provided us a really interesting perspective, and he reassured us along the way that